Hi, and welcome to the latest of the Kavli Foundation's Spotlight Live webcasts, which offer you a chance to hear from scientists on the cutting edge of discovery. My name is Adam Hadhazi. Today, we're going to talk about a bold proposal for a Super-Hubble space telescope that could take our search for alien life in the universe to a whole new level. Astronomers believe there are dozens of Earth-like planets, worlds around other stars, right here in our cosmic neighborhood. The problem is that many of these nearby exoplanets are far too faint for the Hubble Space Telescope and even its planned replacement, the James Webb Space Telescope, to see and study. That's too bad, because the light from these worlds' atmospheres might contain chemical signatures that can only be put there by extraterrestrial life. In order to capture this light, and maybe finally answer the profound question of, are we alone in the universe? What astronomers therefore dearly want is a Super-Hubble, a giant next generation space telescope. Joining us today are three scientists who want to create this revolutionary instrument. Known as the High Definition Space Telescope, it would boast a mirror 25 times the size of Hubble's and twice that of James Webb's. This gargantuan mirror would grant the High Definition Space Telescope, as its name implies, the power to see the cosmos in HD. Just like how modern televisions bring strikingly clear pictures into our living rooms compared to those boxy sets and their grainy screens we used to have to squint at. Such a telescope could not only discover alien life on exoplanets, but it could also dig deeper than ever before into cosmic history. With it, we would get to witness when the first stars and galaxies took shape and began churning out the elemental ingredients necessary for life. But okay, before we get ahead of ourselves here, we should note that the High Definition Space Telescope is only in the concept phase for now, and it probably wouldn't launch until the 2030s. Joining us today to discuss the promise and challenges of such a game-changing instrument is Julianne Dalcanton. She is a co-chair of a July report about the High Definition Space Telescope. Julianne is an astronomy professor at the University of Washington. Her research digs way back in space and time to the origin of galaxies. Joining us as well is Marc Postman, who served on the report's committee. An astronomer at the Space Telescope Science Institute in Baltimore, Marc spends his days pondering cosmic evolution, as well as how to build ginormous space telescopes. Also joining us shortly is Sarah Seeger. She is the other co-chair of the July report. She's an MIT professor and affiliated with the Kavli Institute for Astrophysics and Space Research. Sarah is an exoplanet expert, and she's been called an astronomical Indiana Jones for her seeking of the holy grail of exoplanets, an Earth twin. All right, welcome everybody. Thank you for joining us.
Hey Adam, welcome everyone.
Thank you, Marc, Julianne. And all right, guys, a quick reminder before we get started. If you have a question for our panel, please send it by email to info@kavlifoundation.org or tweet us using the hashtag KavliLive, and we'll get to as many questions on air as we can. I'd like to go ahead and throw out the first question, which is Julianne and Marc. What drew you guys to this project? What is it about the High Definition Space Telescope that would really revolutionize your research? Why would you love to see it become a reality?
I'll take that one, Marc. So I've been a heavy user of the Hubble Space Telescope for more than a decade at this point, and it's a fantastic machine. And I still can't believe some of the things that we've been able to do with it. But with every machine that you use, you always reach the limit sooner or later, right? You always know what it could do better. And the more you use the Hubble, the more exciting ways you find to use it, the more it occurs to you about, God, just how much more we could do if we had that next thing. Now, there's also a big element of paying it forward, in that when I was coming up as a student, I was in graduate school when the Hubble Space Telescope was launched. And just Shazam, there it was, and I could use it, and I could do science, and it was fantastic. But these things don't magically appear. You don't go down to Walmart and pick a telescope up and then just launch it. It takes decades of planning in order to make this happen. And so those of us who have benefited from all of the work that our predecessors did really owe it to start thinking about what is the instrument that we want to have transforming astronomy decades from now, so that future generations of students will have the same experience that we have.
Very good. Marc?
Yeah, no, I have a very similar sentiment to Julianne. I think I remember the first Hubble image I got from my own research, uh, which was so dramatically better than any of the ground-based data I'd had up to that time that I spent the entire day just staring at the image and just, envisioning all this great science that it was going to enable. And that's a key thing, is the ability to actually see fine detail in galaxies that are billions of light years away makes a profound difference in your ability to understand what's going on in those galaxies. And we've done great with Hubble, and James Webb is going to take us, quite a bit further. But even there, where you look about where we need to be in the 2030 era, you realize that both as great as Webb will be and as great as many of our big ground-based telescopes will be, there's still a lot of clarity and depth that we're going to need that we just don't have a telescope that can do. And so that's why we are thinking about this one. And in particular, if Sarah were online now, what she would say is that if you really want to look for those Earth twins around other stars, you're also going to need a telescope with this same kind of capability that can really see very faint things, can see them when they're very close to very bright things like the stars they're orbiting, and be able to dissect their light to see what they're made of.
Very good. I think that's actually a good segue into. I'd like to show our viewers here. I want to give them a sense of how sharp the high-definition space telescope's cosmic vision will be compared to the Hubble Space Telescopes. Here we see some simulated images of the same galaxy located 10 billion light years from Earth. On the left side here is how this distant galaxy looks to the Hubble Space Telescope. It's all chunky and pixelated, as you see there. Now on the right-hand side, a Super-Hubble Space Telescope can see the galaxy's whirling spiral arms in exquisite detail, plus make out a dwarf galaxy off to the right-hand side there. With sharper images like this, and guys, let me pose this back to you, what kinds of questions will the high-definition space telescope allow us to answer that we don't have the ability to answer currently?
The question is, where do we start and where do we end, right? We could talk about what this might transform for days.
Well, let me actually then hone it a little bit too. One of the central conceits here about building this next generation space telescope someday is, of course, answering the question of, are we alone in the universe? I want to get a feel for how, looking back deep into cosmic time, like a galaxy's many, many billions of years ago, how will that help us learn more about actually how life arose in the universe? What is the connection between way back then and more in recent times?
Well, so one of the things that we in many ways credit Carl Sagan for making us all aware of is that every atom molecule in our own body was once in the center of a star somewhere. All the atoms heavier than essentially hydrogen and helium were made in the cores of stars. And so the main ingredients for life are all created in the cores of stars, and also during the phase when stars end their lives. And so the big question of how life is distributed throughout the cosmos is intimately tied to how do those atoms like carbon and oxygen and nitrogen get out into interstellar space? How do they form solid bodies on which life can ultimately take root? And how is that process, what's the big connection between that astronomical process and then the biological processes that lead to life? So trying to understand that whole story is what we're trying to do here. And there are key bits in galaxy evolution that we think happen, but we don't know for sure. We haven't directly observed them. And one of those key processes is how does gas that carries those elements away from stars like oxygen, nitrogen, and carbon, how does that, it tends to leave galaxies and stars and then fall back into it. And following that flow is something we'd love to be able to do. And we've been doing it a little bit with Hubble, but only in very small bits and pieces. And HDST would just allow us to visualize that whole process directly.
Excellent. Julianne, anything to add to that?
I mean, just that the story goes back even farther, right? It's not just the processes that happen near a star and the evolution of stars, but how did we even get stars in the first place? You know, we only got stars because enough material made it into a galaxy that the material got close enough together that it could bind together into stars. And that takes us, you know, further and further and further back into time. Now, James Webb will revolutionize our view of some of the very youngest, very most distant galaxies, but that still leaves, you know, billions of years of cosmic time over which we're trying to understand the processes that even lead to the step of getting the stars that you need to host planetary systems and to build the elements that you need to have to develop planetary systems. So there's, with the precision of the view that you would get with HDST, we can actually watch, we can resolve out the scale over which regions turn into stars. Right now, it's just, you could see on those pictures, they were just these sort of pixelated, blurry regions that they were a little blue, and so we're pretty sure that's a region where stars form. But we should be able to resolve out the actual subunits of the little regions in galaxies where stars form. And we'll be able to do that absolutely anywhere in the universe it occurs, which is remarkable and transformative.
Excellent. To go ahead and tackle some of the big issues here of actually getting such a telescope built and up into the heavens to do this important scientific work, what are, as we see it now, some of the biggest engineering and technical hurdles to building a Super-Hubble?
Well, one of the key things we want to do is to be able to image Earth-sized planets in the habitable zones, which is around other stars in the galaxy. And the habitable zone is this region which allows water to exist in a liquid state on the surface of the planet. And we think that's important for you know, making the probability of life a lot higher. To be able to do that, you need to, you're looking for a very faint planet, a planet like the Earth. If we were to go, you know, if we were to go 50 light years away from Earth and look back at the sun, the Earth it only shines by reflected light, and it would, we'd see this little star that was the sun, and then we'd see a tiny dot that was 10 billion times fainter than the sun sitting right next to it, and that would be the Earth. So the challenge for looking for life is we've got to suppress the bright glare of a star that's 10 billion times brighter than the planet you're trying to see. And so that is one of the big technical challenges, is to build an instrument to be able to do that. And such instruments are called coronagraphs. And right now the state of the art of such coronagraphs is they can probably do that starlight suppression by sort of a factor of 10 million instead of 10 billion. So we need to, you know, there's a bit of a step there, about a, you know, almost a factor of a few hundred in performance that we need to get to get to that level. So that's one of the challenges. Now there's been a lot of progress made. People think they know how to design devices that will do this, and so we need to now take it from sort of the conceptual phase to actually building something. The other challenge goes hand in hand with that, is in order to do that, you need the telescope to be very stable and not be changing its mirror positions or its alignment while you're doing that starlight suppression. And it's stable to a very, very, very quiet level. It's remarkable how stable it has to be. And that's also probably another, you know, factor of 100 improvement over where we are today in terms of current stability on space telescopes. So I think those are the two biggest challenges that we have to overcome. The bit about the big mirror is not that as much of a challenge. It's a technical detail.
Yeah. Step in there for a quick second. That was a viewer question, actually, something I'm very curious about, too. With regard to how we're going to get a mirror that size up into orbit and to, well, not orbit, at least get it out into space HDST will be a good ways from Earth, actually. But how to get the mirror into space is you think that's actually not a major issue? And then how might we also avoid having some of the difficulties that we did with Hubble, which needed corrective surgery, basically, to get its optics correct?
Well, the strategy. Marc has talked about some of the technical challenges in the project, but one of the things while discussing it that we tried to look at were ways that we could take advantage of things that NASA already knew how to do. And with JWST is being built out of a collection of hexagonal mirrors that fit together like puzzle pieces to make one larger mirror. And to launch JWST, it's going to be folded up and then tucked inside a rocket. So the problem is you can't make a single mirror that's any bigger than the width of the interior of your rocket. So JWST folds up. So the concept with HDST, and there are other ways you could do this if you had a bigger rocket, but the concept with HDST is that you just put more hexagonal segments around something that's like JWST, and then you fold it up carefully, tuck it in, then it launches into space, and then furls open.
Okay.
Yeah, and actually,
Go on.
With the kind of rockets that are even available today, we already have a design using the same sort of unfolding mechanism that James Webb uses that would allow you to build a mirror like what Julianne just described and launch it in an existing rocket using the same kind of deployment scheme that James Webb will use. So that, while we haven't actually done that yet, it's a technology that's very derivative of something we already know how to do.
Very good. I had a question here about how the high-definition space telescope could be used for right here in the solar system, actually. How could it be used for, say, studying the moons of Jupiter and Saturn that might harbor life in their subsurface oceans?
Do you want me to take that, Marc?
Go ahead. Yeah, sure.
Yeah. So the solar system is a very, very dynamic place, and it's an incredibly interesting place. So in planetary astronomy, the best thing you can do are send probes to go off to visit things and get really close to it. So like with the beautiful pictures we've seen of Pluto, orbiters around Mars, things actually on Mars. And so for things like studying oceans on moons of Jupiter, it would be great if we could actually go there. But that takes a long time. It took 13 years to get to Pluto. And meanwhile, lots of things are happening in the solar system. So with HDST, we would have the resolution that we could watch anything in the solar system even without going there. You could actually get to about 25 kilometers, I think it is, resolution on Jupiter.
Wow.
So that you could actually see features the size of Manhattan at the orbit of Jupiter. Now, the farther away something was, the resolution would be worse, but if it was closer, it could be better. So you could see geysers, you could see volcanoes. The telescope would be very sensitive at ultraviolet wavelengths, so very high energy light. And we think that in the same way we have northern lights and aurora on Earth, we think that we see the same phenomena happening on other planets, and you could actually watch that occur with exquisite resolution at some of the outer planets as well. So I think it's not a substitute for actually visiting the planets, and NASA should have continue to have a strong planetary program. But at the same time, we would be able to make we would see phenomena, I think, that would help motivate where we want to go to next.
Very good. Marc, anything to say on that?
Yeah, no, I think that's right. I mean, and the other thing is that there are, as we know, New Horizons just flew by Pluto, and it's now heading out beyond Pluto to a couple of other sort of very distant things we call Kuiper Belt objects, which are out beyond there and are probably the most pristine material. They're sort of the original material of which the solar system was created, and so being able to understand how many things like that are out there and what they're made of is very key. And the thing is, they're very faint and they're very small, and so you either need to go there like New Horizons is doing, which you can't do that often, or you need a big telescope to try to see them. And that's another area where HDST would really be able to do some very interesting observations in terms of studying those very distant and small bodies that are orbiting beyond Pluto.
Excellent. A question that I'm sure the viewers are wondering about, and we touched on this a little bit earlier, but why are we talking about a telescope that won't launch until the 2030s at the soonest? We could have like 5 new U.S. presidents before this telescope is ever up there in space. Well, why do this report now? Why start the process?
Well, I think Julianne hit upon this. These are big projects, multi-billion-dollar projects, and they take a lot of planning and in some cases technology development, and NASA's doing more than one thing at a time, and so it has to sort of spread out how it invests its science funding. It can't all go to one project. So as a result, these things do tend to take a couple decades to go from the initial concept phase to the initial design phase to the construction phase and ultimately to launch and operations. And I wish we could do it quicker, but we have lots of things that will keep us busy in the interim. So I think, now is given that reality, you have to start now to think about what you want 20 years from now.
I think another area where it really helps is in terms of if you have an idea of what your goal is, you can start developing the technology now. So in the same way, you're not going to retire until you're in your 60s or 70s, barring the lottery. And so you start making plans now about what you have to do such that you can eventually reach this goal at some time in the future.
Gotcha. Very good, guys. Next thing I want to ask about, let's try to spell out a little bit more for the viewers about how we think that the high-definition space telescope could be our best thing yet when it's up and doing its work. It might be our best way yet at finding evidence of little green men, women, or whatever, if you will. Try to give us a sense of how it would be even better than, say, the biggest ground-based observatories we have in the 2030s.
Yeah, so it will be a significant advance over any telescope we have now or even on the ground in the next decade. And there's a number of reasons, one of which is in order for ground-based telescopes to achieve their clarity, they have to correct for the atmosphere, which is changing. It's making the starlight twinkle, every 10 or 20 seconds it does something different. And you don't have that in space. And so that, even if they can correct for that, that correction you can do on the ground is just not enough to be able to do that kind of 1 part in 10 billion starlight glare suppression that you'll need to do to see an Earth-like planet around many different kinds of stars. And HDST will have that stability and capability to see hundreds of star systems. Now, it's not to say the ground won't be able to do some stars. The ground probably will be able to study pretty cool stars, like, and by cool I mean low temperature stars, small stars, and perhaps detect the planets in the habitable zone around there, but only for maybe a handful. And if we're trying to actually look for life, if you look at Earth's spectrum, and you can see in the atmosphere of our own planet, you see sort of these signatures that life is present. You find evidence for oxygen and methane and water all coexisting in the spectrum at the same time, which is a pretty strong indicator that there's some biological process going on. And if you're on the ground looking through that same atmosphere that's full of these biosignatures, you have to first subtract all Earth's biosignatures out of the way before you see the ones on the planet. And that's not easy to do, especially if you're looking at another planet like the Earth. So if you're in space, you don't have that problem because you're well above the atmosphere. So those two things, I think, are a key thing. And then once you're in space, the number of planets you can look at goes as sort of it really increases dramatically as you make your telescope bigger. And so we sort of thought about a telescope that would be able to find dozens of potential Earth-like planets around other stars. And that's why we picked the size we did.
Very good. Julianne?
Just to add in, I mean, we would have loved it to be 20 meters across or 30 meters across, but at some point you just can't pack it into anything. Right? There's only so many suitcases you can put in your trunk. There's only so much mirror you can fold up inside a rocket.
Right. And 12 meters, range of 11.6, I understand, as the report talks about. That seems to be the kind of sweet spot here, correct?
I think so.
Very good. All right, guys, so it's time for one last question here. And I think this may be the hardest one, so just warning you. Most major space telescopes are eventually named after famous planets, like Hubble, of course, and Tycho Fermi, Lyman Spitzer, or important figures in space research, like James Webb, a former NASA administrator. If you guys were to offer suggestions for the high-definition space telescope's official name down that road, what would be your telescope? Or choice, to make it easy.
I would think Sagan would be the contender.
Yeah, I would agree. I think the Carl Sagan Space Telescope is something I've contemplated as, you know, he was one of the first people to think about, you know, studying the atmospheres of our planets in our own solar system, and then how that might be useful for looking at planets in other star systems. And so certainly a very worthy namesake for such a telescope.
What do you think, Julianne?
I come to exactly the same conclusion. I think that's a very natural name. The only question is, if something like this wouldn't launch until the 2030s, you know, someone else may have snatched up the Sagan name beforehand.
Yeah.
I don't know if we can save it that long.
That's true enough.
I think it does have a nice ring to it, the Sagan scope, or even the Super Sagan scope. I'm a fan. I definitely think that would work. Well, fingers crossed. We'll see what that turns out to be, if indeed the project gets off the ground. Best of luck to you guys on your continued work on the project. We're going to go ahead and wrap up. Unfortunately, because of technical difficulties, Sarah was not able to join us today. Very sorry about that, but hopefully we can get her in on another Hangout soon and ask her some more questions about the exciting search for alien life. All right, we're going to wrap up, guys. This video will be appearing on the KavliFoundation.org website. You can also check it out on Kavli's YouTube channel. And that is all. Thank you very much for your time today.
Thanks, Adam. Thanks, everybody.
See you guys.